Welcome to This Explainer. Okay, today we're diving into the absolute building blocks of coordinate geometry. And look, rather than just seeing this as abstract math on a whiteboard, I want us to view this as a giant city map. It's really just a set of navigational tools that we can use to solve actual real-world problems. By the end of this, we're even going to model the exact cost of a taxi ride. So let's jump right in.
Here is our roadmap for today. 1. Mapping the Cartesian plane. 2. Steepness and understanding the gradient. 3. The equation of a line. 4. Parallel and perpendicular lines. And 5. Real-world math modeling.
All right, starting with section 1, mapping the Cartesian plane. This is all about finding your address. Well, every map needs a center point, right? In our Cartesian city, that's called the origin. It sits perfectly at 0, 0. It's the exact intersection of our main highways, the horizontal x-axis and the vertical y-axis. Think of it as the absolute anchor for every single journey we're going to take. Now, your location on this map is always pinpointed as x, y. You always make your horizontal movement along the x-axis first, and then follow it up with your vertical movement along the y-axis. Seriously, do not mix these up. Reversing them is actually the most common navigational error people make.
So these intersecting axes slice our entire map into 4 distinct quadrants. And the cool part? By just glancing at whether your coordinates are positive or negative, you instantly know which neighborhood you're heading toward, without even having to plot the point. It's a really great shortcut.
Moving right along to section 2, steepness. Understanding the gradient and how to move.
You know how some roads are a breeze to walk up and others leave you totally winded? Well, the steepness of any path is its gradient. We represent it with the letter M. It is simply the vertical change over the horizontal change. You'll often hear this called rise over run, or mathematically, y2 minus y1 over x2 minus x1.
These gradients totally dictate our terrain. A positive gradient means you're hiking uphill. Negative means you're cruising downhill. A gradient of 0, that's a perfectly flat road. But what about a perfectly vertical line? Well, mathematically, that gradient is undefined. It's literally a sheer cliff face on our grid. No way you're driving up that.
Okay, let's actually see this formula in action. Say we want to find the gradient between the points 1, 2, and 4, 8. We just plug the y values in on top and our x values on the bottom. So 8 minus 2 is 6, and 4 minus 1 is 3. 6 divided by 3 gives us a gradient of 2. That means for every 1 unit we move across, we rise 2 units up. Simple, right?
Section 3. The equation of a line. Writing our driving directions.
Okay, this is absolutely crucial. Every straight road on our map follows this famous formula, y equals mx plus c. Remember, m is our gradient, that steepness we just talked about. And c? That's our y-intercept. It's the exact spot where our road crosses the vertical axis. So if we see y equals 2x plus 3, it means our line is rising by 2, and it crosses the y-axis right at positive 3.
Finding these crossing points relies on this really brilliant, simple mirror logic. If you want to find the y-intercept, you just set x to 0. And to find the x-intercept, just do the exact reverse, set y to 0. It works perfectly every single time.
Section 4. Parallel and perpendicular lines. Let's look at how cars interact on these roads.
Parallel lines are like train tracks. They stretch on and on forever without ever touching because they share the exact same gradient. They're perfectly synced up. Perpendicular lines, on the other hand, slam right into each other to create a perfect crossroad, meeting at exactly 90 degrees.
Now, for perpendicular lines, there's a magic number you have to remember: -1. If you multiply the gradients of 2 perpendicular lines together, the result will always be -1. To find that perpendicular gradient, there's a super quick trick. You just take the reciprocal of your original gradient, basically flip it upside down, and then change the sign. So if your original road has a gradient of 3, the perpendicular road's gradient is -1/3. If the original is 5, the perpendicular is -1/5. Just flip it and reverse the sign.
And now, Section 5. Real-world math modeling. Paying for the ride. Let's bring this all together.
Let's hail a cab across our grid city. Say a taxi charges a fixed base fee of 50 rupees just to get in the car. Then it's an extra 10 rupees for every single kilometer you travel. We can model this perfectly with our y equals mx plus c formula. The total cost is our y, the distance we travel is our x, that 10 rupees per kilometer, that's our rate of change, our gradient, the m. And the 50 rupee fixed fee is our starting point on the meter before the car even moves, which maps exactly to our y-intercept, the c. Put it together, and our real-world equation is y equals 10x plus 50.
So what's the cost for a 6-kilometer ride? Well, we start with our equation, y equals 10x plus 50. We plug in 6 for our distance, x. 10 times 6 is 60, plus the 50 base fee, boom! We immediately calculate a total cost of 110 rupees. We've literally just mapped reality onto a math grid.
Okay, almost done. But first, avoiding the potholes. Let's look at some common mistakes.
Here is a rapid-fire list of traps you definitely want to double-check in your work. Number 1, writing coordinates backwards as y, x. Don't do it. Number 2, jumbling the gradient formula. Just remember it's always the change in y divided by the change in x. Number 3, mixing up your gradient m with your intercept c. Number 4, overthinking parallel lines. They always have equal gradients. End of story. And number 5, forgetting to reverse the sign when you flip the fraction for perpendicular lines. Watch out for these potholes, and you're going to be absolutely fine. Which brings us to the very end of this explainer. We started with a simple grid, moved on to steepness, mapped out our streets, and even calculated a taxi fare using pure algebra. But I want to leave you with a quick thought before we go. If a linear equation can perfectly model a taxi ride, how might you use y equals mx plus c to model your monthly phone bill or a gym membership with a joining fee? Math isn't just trapped on paper, guys. It is the hidden structure behind so much of our everyday lives. Thank you so much for joining me to figure out the building blocks of coordinate geometry, and I will see you in the next explainer.